All right, you guys ready? So exam 2 happened. There were some interesting questions, but more, so a lot of the questions were, in my opinion, straightforward in the sense that you could sort of predict the answer before you even start doing the problem. Problem 7 was a little bit lengthy, and that's what I've heard from people, and that's what intention was, a little bit of a challenge. But overall, from the exams that I've given for signals, this was a very straightforward exam. So if you have not done really well on exam 2 for signals, then we have some serious issues. Going forward with your technical electives, that is not a very good sign. So we are doing the grading right now. We hope to finish the grading by Monday of next week. So Monday, I'll be discussing grades. And if I've already posted solutions on Piazza, so you're feel free to take a look at the solutions, see what you got right or wrong. I know there's a deadline tomorrow, right? What deadline is tomorrow? There's a pass-fail deadline tomorrow. Pass no credit or pass, whatever the deal with that is. So you can take a look at the solutions to get an assessment of how your grade is going to turn out. So while that is going on, we need to move ahead with our course. We are talking about sampling and reconstruction. Oh, by the way, I forgot to mention, homework 15 was due tonight, but because we have nothing due on Monday of next week, I'll push it out to Monday of next week. So that is going to get changed. So you don't have anything due tonight, essentially. But to be fair, homework 15 is not that long. It doesn't take you that much time to finish that. So if you want to finish it tonight, you have that option. Or you can continue working on it until next Monday. Let's see. Questions or concerns? Homework, exam. I saw some really interesting approaches to some of the problems, even better than my way of solving them. So I was really pleased to see some creativity come out in terms of Fourier transforms or inverse Fourier transforms. Some solutions were very elegant. So I like that. And those who did that, I already pointed that out to them. Okay, let's continue with sampling. So after communication systems, we started talking about sampling. Why? I don't want all my signals. I just want some values in my signal. So I'm going to make it into a discrete set of samples. And then I'm going to, at a later point, use those samples to maybe play it on a speaker, right? So music, discretized, and then later on, eventually, you play it on a speaker. So at some stage, they need to be converted back into their continuous form, which means that I need to reconstruct the signal using those set of samples. So that's what we were talking about. And the way we sampled the signal is just multiplying in the time domain with the impulse train, right? So x of t was our continuous signal, such as your voice, and you multiplied that with an impulse train. And because you multiplied that by an impulse train in time domain, you convolved the Fourier transform of x with another impulse train, right? So multiplication in time, convolution in frequency, impulse train in time, impulse train in frequency. Using those two criteria, if your x of t has a Fourier transform of a triangle, like that, just one guy, when you sample it, you essentially convolve one triangle with a bunch of impulses, right? Those impulses are going to appear at frequencies corresponding to the sampling frequency. So if you look at sampling frequency in radians per second, say omega s is going to equal 2 pi fs. And fs is going to be 1 over ts. Fs is your sampling frequency, ts is your sampling time. So as you reduce resolution in time, or make the sampling time smaller and smaller, you are increasing the sampling rate. The fs is increasing, and hence omega s is increasing, which means as I'm reducing my resolution in time, these triangles are moving farther away in frequency, right? So you're getting more and more separation between these triangles as you reduce sampling time. So the faster you sample, the better it is going to be over here. In terms of what? Well, in terms of aliasing, right? So if you sampled very slow, meaning TS is pretty high, then these triangles are going to be close to each other, something like that, and the higher frequency content is going to get corrupted because of those triangles overlapping. However, if you pick the Nyquist rate, which is do it at least twice, or Nyquist rate is exactly twice. If you do it exactly twice, then what you have is these two triangles exactly touching each other. Because this one is omega m. What is omega m? Omega m is the highest frequency component in X. And because you sampled this at omega s, the center frequency of your second rectangle is going to be at omega s. The bandwidth of the signal doesn't change. So here it is 2 omega m. So here it should also be 2 omega m. So which means this point is omega s, this point will be omega s minus omega m. So if you sample these 2 points, are they touching each other? Are they separate from each other, or are they overlapping? Overlapping is bad, which means undersampling. You didn't sample it fine enough. So reconstruction is not going to go well. If you sample it at Nyquist, they touch each other, which essentially means omega s will equal to omega m. Sample it at least twice the maximum frequency in the signal. You cannot pick any frequency in the signal. You have to pick the highest frequency in the signal. Next, so if you sample it, that's what your spectrum looks like. And we talked about this in the last class. From this, how do you reconstruct? We talked about 3 strategies. One was first order hold, which was essentially connecting the dots, linear interpolation. The second was zero order hold, which means like a staircase waveform. I'll hold the sample until I get the next one. The third was sinc interpolation, or ideal reconstruction, which means I will superimpose a sinc on each sample and I will add up all those sinks. The best sort of reconstruction. The reason is the sinc, because of those zero crossings, the zero crossings happen exactly at the time you get the next sample. So the sinc doesn't contribute to the next sample, or any sample actually. Right? So if it is sinc, where is it in sinc? Time domain, which means in frequency it's a rectangle. And that rectangle, your ideal reconstruction filter, is essentially an ideal low-pass filter. So if you send those sampled waveform through an ideal low-pass filter, you're essentially reconstructing the signal, right? So you go through this, which means in time you're convolving what with what? Let's do this. What are you convolving with what in time? A sinc function, yeah, with what? Set of samples, right? So you have a set of samples and you're convolving that with sinks. What is it going to look like in time? It is going to look something like this, right? Like that. Each sample has a superimposed sinc. Each sample has a superimposed sinc. And when you add all of those up, you get your continuous signal, right? Let me go back here to this. All right, so you got the reconstruction filter. I have chosen a height of t over here so that eventually I get a 1 for the amplitude exactly matches your input signal. Doesn't matter if you have a 1 over there, then you get a 1 over t over here, which you can fix by using an amplifier with a gain of t. You can fix that. So how are you going to choose the cutoff frequency of this ideal low-pass filter? You know that this triangle has to get through, but you also know that this has to be rejected. So which means that you are going to pick an omega c, the cutoff frequency of your low-pass filter, such that it is greater than omega m, but it is less than omega s minus omega m. So you can put it exactly in the middle, which is omega s divided by 2. Sampling frequency divided by 2, that's how you can set up your cutoff frequency of the low-pass filter. So your reconstructed waveform has exactly the same Fourier transform as the original waveform before you sampled it, which means if you follow Nyquist, you can sample and reconstruct to get back the signal. Questions here? Okay, let's move on. Nyquist criteria, sampling rate has to be greater than twice the maximum frequency in the signal. When I say frequency, because I'm showing omega, you guys know based on context that I'm referring to radians per second, right? But this applies the same way to Fs, right? So this also implies that Fs should be greater than 2Fm, right? Just a factor of 2 pi getting canceled out. So that's what is going to set up my criteria to find out, okay, I need to reconstruct, so what frequency should I sample it at least twice the maximum frequency of the signal. So if somebody is screaming at 2 kilohertz and you want to sample it, then you at least need to sample it at 4 kilohertz, right? Or maybe you don't want to hear all their screeching sounds, you sample it at lower than that. You lose all the higher frequency components, so it doesn't bother your ears. All right, let's move on. Nyquist sampling criteria is going to be 2 times your omega m. We talked about that. Now let's talk about the effect of phase. We said sampling rate has to be twice the maximum frequency of the component, which essentially translates to you need 2 samples in one time period, right? So if you have one time period, you need 2 samples. So the question is, does the location of those samples matter or not? And it very much does. Let's take a look. Here we are choosing omega s to be greater than 2 omega m, which means that we are better than Nyquist. We are oversampling, so we should be good. Consequently, if omega s is greater than 2 omega m, Ts will be less than Tm divided by 2. Can anybody tell me what Tm is? What is Tm? Ts, you know Ts, right? That is essentially timing, sampling time. How fast are you sampling the signal in time domain? You are getting the samples at 1 Ts, 2 Ts, 3 Ts, and so on. So that's Ts. What is Tm? It is the time period of what? Highest frequency component, right? So it is the time period of the highest frequency component in the signal. Time period that corresponds to highest frequency in what? In x of t, the signal that you're trying to sample, right? So if omega s is greater than 2 omega m, then you can write omega s in this way, omega m in this way. Do some manipulation here to get Ts should be less than Tm divided by 2. So to recover x of t, we need more than 2 samples per period, right? Tm is the time period of the signal corresponding to half. This is less than half of that, right? So you at least need 2 samples in one period. So the samples, so here you have a cosine omega mt. It has only one frequency, omega m. Where are you going to get those 2 samples? So if I look at one time period here, let me highlight that one time period in yellow. So I start here, I go down, and I come back up. That's one time period, right? In one time period, I need 2 samples. Where are you going to take those 2 samples? Well, you could pick the samples here and here, right? That's two samples in one period. Will you be able to reconstruct the cosine with those? No, absolutely not. All you have is 0, right? No matter which reconstruction technique you use, you are going to get a flat line, right? So that's not going to work clearly. We need a better strategy. So let's try to see what happens as you're moving this to a different spot. So let's say we move this to here, here, and here. Do you get a cosine? Just think about that. If you did linear interpolation, you would get something like this, right? So it's not really a cosine, but it is getting there, right? So if you started looking at minimum squared error, what is the amount of error that you have when you sample and then use those samples to reconstruct the signal, right? Essentially the difference between the cosine and this linear interpolated line. The minimum mean squared the mean squared error is going to keep going down as your samples go from both being at 0 crossings to being at exactly the peaks, right? So if you go to the peaks, that's when you will get let me write here. If you go to the peaks, now you have 2 samples per period. And if you did linear interpolation, you would get something like this, right? And if you did ideal reconstruction with sincs, you would get a cosine. Very smooth, right? So that's the effect of phase. You have this impulse train that you're multiplying the signal with. If the impulse train is, such that it is matching with the peaks, you're good. But if it is moved, if there's an effect of phase, if it moves such that these are lining up with the zero crossings of the cosine, you will not be able to get the signal. You guys see that? So there is the output, we can say this, right? The output is going to be determined by the phase of that impulse train that you sampled the signal with. What are these highlights over here? Let's just talk about them. This is 0. What is this? This is TS, 2TS, 3TS, right? These are locations in time where you evaluated the samples. That's where you sampled it. So if you sampled it here and here, you can see that you're not going to get anything. But you still have obeyed Nyquist, right? You still are taking care of Nyquist, but you are not able to reconstruct because of the phase of that impulse train. Questions here? All right. Over here, what kind of a signal do we have? We have a sinusoidal signal. How many samples do we have in one time period? Come on, everybody is going to say what? 4 samples per time period. Are we obeying Nyquist? So we should be able to reconstruct it, right? So the reconstruction is going to look like what? Let's suppose we do linear interpolation. Yeah? Yeah, you're getting it, right? And if you did sinc interpolation, you would get a very, very good sinusoid signal. How does it look like in terms of the impulse train that you multiply it with? You have an impulse train. What can we say about the time here? This is going to be 0. This is going to be TS. This is going to be 2TS. This is going to be 3TS, and so on. Yeah. And what about this? If this is 0, what is this point in time? The time period of the signal, right? And in this case, this is the only one frequency. So this is the highest frequency. The time period that corresponds to that is going to be Tm. So what can we say about the relationship between Tm and Ts? Well, this is going to be 4Ts, and you can see this will line up, right? So 4Ts is Tm, right? Which essentially is right here. Ts is Ts is equal to Tm divided by 4, which is less than half of Tm. So we are good, right? So we are obeying Nyquist. We have more samples than we need. What are we doing? Oversampling. By how much? By a factor of 2. We needed 2 samples in one time period. We have 4. We have oversampled the signal by a factor of 2. So we will be able to reconstruct it. Now, as you are increasing the number of samples in one time period, the effect of the phase is going to reduce, right? Where you take those samples is the tolerance to that is going to improve. Let's move on and take a look at another case where you have slightly different set of samples. So you have in one time period, well, let's take a look at 2. Let's take a look at 3. All right, you have 3 time periods here. How many samples do you have? 1, 2, 3, 4, 4 samples, right? So 4 samples in 4 samples per 3 periods, right? You guys see that? So that is going to evaluate to what? Well, if this is, what is this point going to be? This is going to be your Tm, 2Tm, 3Tm, 3Tm over here. And if your sampling rate is your vertical lines that are dashed, you have 0, 1Ts, 2Ts, 3Ts, 4Ts, 5Ts, 6Ts, 7, 8, 9, 10, 11, 12. 12 Ts equals 3 Tm, which implies 3 Ts equals, did I do this right? Oh, no. This is not Ts. This is my Ts. This is the 0, TS, 2TS, 3TS, 4TS, right? So TS is going to be 4T, this is 4TS. 4TS is, so TS equals 3 divided by 4 TM, right? So it is greater than half TM. So we don't have enough. And you can clearly see that. When you start reconstructing, you are reconstructing something like this. Not a cosine or not a sinusoid with that particular frequency. What components got messed up? The high frequency components got messed up. You can see that, right? We had higher frequency than what we are sketching. Those got messed up, so we are left with the lower frequency content. You see that? So when aliasing happens, when you don't sample it high enough and those triangles overlap, you get corruption in the higher frequency components of the signal, not the lower frequency components. Right? The lower frequency is still there. So we undersample the signal. You do undersampling, you will not be able to reconstruct the signal with the set of samples that you have, no matter the phase. Questions? Ideally, you are oversampling, but not by that much. Why? Because the higher you sample, the farther away the triangles are. The farther away the triangles are, you will get out of band noise to come in through the filter, right? So there is going to be out of band noise over here and here. Cutoff frequency is half omega s. So the bigger the omega s, the more space that is going to be in the spectrum over here to allow out of band noise to get through. Also, the higher that you sample, you are essentially not using that spectral resource for something like doing a FDM, right? So you don't want to go too high. You want to be very close to twice the maximum. Let's see. But if you are twice at maximum, exactly twice the maximum, then it puts pressure on your reconstruction filter. That has to be sharp then. Let's see. Let's continue. Right, undersampled. Here we have another case similar to what we saw before. 2 time periods, 3 time periods. In 3 time periods, you have 1, 2, 3 samples. And if you extend it out, it looks like you have 4 samples in 5 time periods, which essentially evaluates to TS being 5/4 of TM. What can we say about this? We don't have enough samples, right? This is way undersampled because you see, this is what you will reconstruct. More higher frequency components got lost, right? So way undersampled. So the overlap between those triangles that we imagined is even more. Questions here? What we need is TS to be less than or equal to TM divided by 2, right? That's what we need. We don't have that. 5/4 TM is very, the time resolution is very weak. Okay, now let's talk about some reconstruction filters, right? So 3 types of interpolation, right? Sinc, linear, zero order hold. How do they look like in terms of the filter response, right? So when you are reconstructing the signal, it is going through a filter. What is the impulse response of that filter? Well, you're trying to reconstruct this, right? You're trying to reconstruct X from its set of samples. What is the set of samples? Well, X evaluated at NT, where T over here is standing for TS, right? NTS. And you're multiplied with an impulse train, which is also at NTS, integer multiples of TS. So T or TS, they're both the same in our context here. And you add up all of them, you get the sampled signal. If you want to reconstruct it based on sinc interpolation or ideal reconstruction, we said it has to go through a low pass filter. So here you have a frequency response of the low pass filter, cut off at omega c, hopefully it is greater than omega m. We set it to omega s divided by 2, and then you get your reconstruction filter. Well, how can you write it mathematically? Well, you see, this guy has a bunch of delta functions. It is going to get convolved with the impulse response of this guy, right? So if I have h sub cap h of r of omega to indicate the frequency response of the filter, I can also say h of t is its Fourier transform. So R here, right? So I know HR of omega is a rectangle, so you guys can tell me what the shape is going to be for the sinc. Went too fast there. You all right, what was the question supposed to be? In frequency, it is a rectangle. What is it going to be in time? A sinc, right? So let me talk about H. If I just leave H, these are a bunch of delta functions. These are getting convolved in time, right? So you have a time function that is convolved with that. So we know the property of convolving with impulse functions. The signal just comes over there, right? Like it's a time shift. So you will have, instead of delta, you will have H at those times, at NTS. Now, how is that going to look like? It is going to look like this. Sinc your impulse response. The amplitude is getting adjusted by x of nt because of this. And you add up all of that, right? All of those sincs. So the sincs are located at integer multiple of ts. Their height is adjusted based on the amplitude of the sample value at those integer multiples of ts. And then you add up all of them. You add up all of them, you get your reconstructed signal. In this case, it'll look like this, right? So it doesn't look like this, right? You don't add up like this, because here, this is adding up to this, right? So the overall signal will be very smooth. So a lot of times students think that it's going down, so this should go down. No, it doesn't. But there is contribution from the red signal here. There is a contribution from the blue signal here. So it'll come up. There will be continuity. Characteristic of real signals. Let me go back. So what do we have in terms of the impulse response? Well, rectangle, take the inverse Fourier transform. You get h of t. And we have done this exercise. You get a sinc. And it's an even function, so there is no need for even a time shift. It's going to be a real impulse response over there. T corresponds to the sampling time. Omega c corresponds to the cutoff frequency of the ideal filter. And that's it. That's your impulse response of the ideal low-pass filter. I'm going to pick omega c such that it is half of omega s, just so that I'm right in the middle of the first triangle, the centered, and the first triangle that comes at omega s, right in the middle there. Omega is divided by 2. Omega s is 2 pi divided by ts. You know that. So h of t, if you substitute this for omega c, simply comes out to be a sinc. So the impulse response is going to be a sinc. Substitute sinc over there for h, you get the reconstructed signal in the time domain is going to be a summation of a bunch of sincs that have been weighted with the samples of x, right? So x of 0, sinc at 0t. Sinc at t minus 0t, which is right in the middle at 0. And then you have x of 1, x of 2, x of 3. Those will be the amplitudes of the sinc. Where is the sinc present? 1ts, 2ts, 3ts, and so on. You add a bunch of them, you get your reconstructed signal. So over here, we are essentially, in terms of the impulses, we are showing the impulses at integer multiples of ts that have been scaled by the amplitude of x at that time. You multiply it with a sinc, because that's what convolution indicates. You have a sinc there, and then you add up all of them, you get that continuous signal that is like this. Right? So you started off with that blue highlighted signal, you sampled it in time, you did whatever you wanted to with that, right? And then at the end, you wanted to, say, reconstruct it so that you can play it on a speaker, you pass it through an ideal low-pass filter, you will get it. Where are the sincs located? 0, t, 2t, 3t, that's where they are located. The best thing about a sinc is what? The contribution from the sinc that is centered at 0 to the next sinc is 0. In fact, its contribution to all the other samples is 0, right? That's what makes this work. Questions here? Straightforward? All right, let's talk about zero order hold. There are two more interpolation techniques, right? Zero order hold, staircase, or the linear order, linear interpolation, which is first order hold. Just connect the dots. So if you have zero order hold, what is the impulse response going to look like? Well, you want to simply hold the waveform until you get the next value, right? So that is going to be hold it until you get the next value at t, or 2t, or 3t, or in this our case, ts is t. Right? So the impulse response of this guy is simply going to be a rectangle, because if you take a bunch of samples of x and you convolve it in time with this, you get that. And then you sum it up, right? So instead of summing it up with a bunch of sinks, you're summing it up with a bunch of rectangles. But the rectangle over here is not centered at 0, right? So you will get a phase shift, e to the minus, and in this case, what is the phase shift? Is going to be t divided by 2, right? E to the minus j omega t divided by 2. That will be there in the frequency. What will be the shape of this zero order hold filter? The frequency response, what will the shape be? It will be a sinc, right? So it will be a sinc right here. You have a sinc function. And because of that phase shift, you got this term, right? Because of this shift, you got that term. And because it was a rectangle, in frequency, it was a sinc. Now, how is the interpolation looking like? At 0, you have this particular sample of x. When you reconstruct it, just hold it until you get the next one. Hold it until you get the next one. Essentially, you're convolving each impulse with the impulse response of this filter indicated as h sub 0 of t. And it is zero order because it's continuous. Like there's no slope to it. There's no quadratic function. It's zero order. Now, in frequency, what does that look like? It looks like a sinc. We know, like if you are given this function, you just put it in any computer program, scan omega, plot the magnitude, you will get this, right? I'm only interested in the magnitude of the frequency response. Why am I not interested in phase? Well, the phase response over here is simply going to be a linear response, right? In terms of omega, it is t divided by 2, right? It's not t squared, it's t divided by 2. So as your phase is linear. And I'm not worrying about that. I'm simply worrying about the shape of the magnitude response. It's going to be a sinc. So what is it? Instead of cutting off in an ideal manner, it is doing this. That is a sinc. And because I'm doing magnitude, everything looks positive, right? Otherwise, the sinc goes below. I'm doing an absolute of this, the magnitude of this. Now, where is the ideal filter in comparison? The ideal filter is this guy, what we had earlier, for which we picked cutoff frequency to be omega s divided by 2. But as you move this to omega s, what do you have? As you move this to first order hold, you have a sinc function. Your cutoff frequency is still here. You see, you are going to have some overlap over here and here with your second, third, fourth, which essentially says this is not going to do as good as the sinc interpolation, the ideal reconstruction that you did earlier. You see that? All right. So here, and this is your 3 dB cutoff. So at cutoff frequency, what is the magnitude of the frequency response? We all know that that's the cutoff frequency of the filter. It is 0.6. That's the function sinc that's indicating that, where t is your sampling time. Next, first order hold. First order hold, what should I be able to do? Well, I should be able to go down between samples linearly, or I should be able to come up, right? I should be able to go down, or I should be able to come up. So what do I do? Over here, I will convolve every sample, every delta that has been scaled with a triangle. And the width of this triangle will be 2t, so, or 2ts, negative ts to ts. It will have a height of 1. So when you do this, what do you have? This triangle here, triangle here, triangle here, triangle here, and so on. Actually, I should put triangle here, right? And then triangle here, and triangle here, and triangle here, and so on. When you add all of them up, you will get essentially a linear interpolation, which means connecting the dots. So that would be the impulse response of this first order hold filter. Its frequency response will be the inverse Fourier transform of this guy. So that's it right there, sinc squared, right? Let me just highlight that. You take the inverse Fourier transform of a triangle, you get a sinc squared. And this guy is centered at 0, so you're not going to get any phase term there, any complex value there. You sketch it against the ideal filter. What do you have? Ideal filter is this, where the cutoff frequency is half of omega s. And now we have h1 of omega, which is this guy. This is your sinc squared function. But notice what happened here. Your cutoff frequency is now 0.4053. Earlier it was 6368, right? So in other words, now it is doing a better reconstruction compared to the zero order hold filter. So zero order hold is going to be sort of the worst among the three, then linear, then your sinc interpolation. You're still losing something over here in the signal. You're not capturing all of that. All right, let's talk about these three cases where we are sampling at different rates. At the top over here, we have the Fourier transform of the signal that we have sampled. Right? This is x of omega. We have not sampled it yet because I don't see any other triangle there. I just see one of them. So I've not sampled x. The maximum frequency is omega m. When I sample it at oversample by factor of 1, which means what? Exactly at Nyquist. So omega s is 2 omega m in that case. Triangles will just about touch each other. If I increase the sampling rate by 4, we said that triangles are going to move farther out, right? That's what you see over here. This is omega m. This is at 0. If I sample it at omega s, this guy becomes omega s, the center of the next triangle. And in this case, the sampling rate is 4 times Nyquist, which means 8 times omega m. So if this is 0, this will be at 8 omega m. In other words, all of this is essentially the spectrum that you have essentially wasted, right? You have not put anything there. For this, the cutoff frequency, what will you choose? You will choose somewhere here, right? That's the cutoff frequency of the filter that you will choose. All of this has been wasted in that case, right? You could have put another signal there. So that's the consequence of choosing a really, really high oversampling rate. You don't need to do that. What is next? Oh, that's just the cutoff frequency of that filter, right? If you need this and this, you would need to have the filter that does that. Because I need this piece and I need this piece. So to get both pieces so that I can reconstruct, my magnitude of the filter would need to be sort of that. All right, so this completes our quick discussion on sampling and reconstruction. Important points over here: 3 types of interpolation techniques in first order hold, zero order hold, and linear interpolation. How do they look like when you're doing the analysis in time domain and frequency domain? Those were the ideas that I wanted to focus on. Next, I'm going to move to our major topic of Laplace transform. Stop recording and start recording in a new video.